Okay, so last week we got introduced to um, using Aspen Plus. So we focus more on the properties um, environment. So let me just quickly go back there. So we focus more on the properties environment. We looked at how we can specify our compounds. We looked at how we can determine the properties of the compounds and how we can estimate, especially the thermodynamic and then the transport properties at different conditions. So that was a major focus for our discussion last week. Today, we want to move into the simulation window itself, where we can connect the different units and then run our simulation. So for the simulation environment, we have different kinds of units. The common units that we are familiar with in chemical engineering or any other related discipline, petrochemical or even petroleum. So we have all these units that we know are mixers, exchangers, heat exchangers, different types of columns, reactors, pressure changers, and separators. And Aspen is very, very good with some of them. So we'll look at how we can use Aspen for them. Now, when we move to the simulation window, we would see these units and these equipments and options available to us. So we find them under what we call the model palette. So I'll show that to us very soon. We have different kinds of things that we can work with, and we'll become familiar with them as time goes on, right? And these are just the descriptions of what some of them are used for. So as time goes on, we'll get used to them. Now, with Aspen, we have some of these blocks or some of these models that are detailed, and some of them are shortcut models. What we mean by that is for some of them, you don't need so much information. So, for example, you just know that you want to increase the pressure of a certain fluid. You know the outlet pressure, you just place that information in Aspen and you are good to go, right? Or maybe you have a particular kind of distillation column. You don't need so much information, just a few pieces of data would be sufficient. But then for the ones that are detailed, they require that you really understand the process and you understand the relevant variables related to the process. So, for example, you might be dealing with a reactor. You might need to know the rate of the reaction. You might need to know the rate constant, the rate expression, all those things, and then feed that data into Aspen. So there are some models that are shortcut models. Sometimes you use them for maybe a preliminary analysis just to start out your simulation to see what you might get. Then for some of them, you can now transition to more detailed models or more detailed blocks where you can feed in the other critical pieces of information you may have. So once again, the more we use the tool, the software, the more we become familiar with some of these things and we know which ones are best for the kind of analysis we want to run. Okay, so when it comes to working in the simulation window, we need to put together a flow sheet. And this is very similar to things you might have come across in the program. So how to design a flow sheet. You know your feed streams, you know your output streams, you know all the units that have to come in between, right? So we are going to do something very similar. And then we would, as we can see, we'll have to select the blocks that we need. We'll have to connect all of them. And then if we want to modify, we can change the blocks, rename them, all these other things that are there. So we'll use this particular example so that we really get introduced to the simulation environment. So I'm sure we'll be able to do parts of the simulation today, and then the rest of it will be done probably next week. So this one says that ammonia is produced from the Haber-Bosch process by reacting nitrogen gas with hydrogen in a 1:3 ratio. However, since nitrogen is obtained from air, it always contains 0.5 mole percent of argon. The reaction occurs at 200 bar and 400 degrees Celsius. Our suppliers are able to deliver the feed at the required pressure, but at the room temperature due to the cost and dangers of transporting a high temperature gas. The process has a single pass conversion of 33%. Hence, the product must be separated and recycled. This we achieve by cooling the product and separating ammonia. However, due to the presence of the impurity, a paired stream is taken before recycling the unreacted feed. Simulate this process for 100 kilomole per hour of nitrogen feed. The temperature of the cooler is to be determined iteratively. We want to recover all the ammonia in the gas stream, leaving the reactor. So what we are saying is that we have a certain process where we have hydrogen and nitrogen being brought together, and they're at a certain temperature and pressure. So we know that we are going to now have to heat it to the reactor temperature, pass it through the reactor, and then some ammonia will be produced. When we are done, we want to recycle it. So we have to do some separation. Then we recycle the unreacted feed back into our process, right? So the first thing we need to look at is what are the compounds of interest. We need all the compounds in our process. So every raw material and every product, if you want to, or if you're expecting certain intermediary or intermediate products, you include them as well. So for this simulation, our raw materials, we have nitrogen, we have hydrogen. We were told that there's argon in the nitrogen stream, so we include argon. And then we know that we are forming ammonia, NH3. So every single component that you are expecting, or every single compound that you're expecting to either be a raw material or to be formed at any stage, you would need to specify it here, or you need to include it here. So even if it's not your final product, but it's an intermediate product, you get to that before you get to your final product. You need to include it here as well. And just like we did last week, from here, the next thing is to go to our property methods or to specify our property method. So we'll click on next, and then we can choose a property method. So we'll be using Penn Robinson. So under P, you look for Penn Rob. We can click on next. This is just Aspen putting together some kind of binary data. We don't need to worry about this, like we said last week. So we can run it, and we have no issues. It says results available. So now that we are done with this, we can come to the simulation window itself. So right under the properties button at the far left, you would see simulation. So we can click on simulation, and it brings us to this interface or this environment. Now down here, we see the model palette you spoke about, the one that has a different kinds of equipment and then units. So we have mixers or splitters, we have separators, exchangers, columns, reactors, pressure changers, manipulators, solids. So all these different things are here, right? For our process, we know that we are working with nitrogen and hydrogen. So what we'll do is that we'll first define the stream, and then we'll include the units as we go. So we'll build it bit by bit. Now, how do we define our streams in Aspen? Under the model palette, you would see this block with the word material written there. So that is for our material stream. Sometimes you may want to work with a heat stream or a work stream or a power stream. So you can click on the drop down arrow and then select what you are dealing with. But what we are working with is a material stream. It is material that we are transferring. It's the flow of material, right? So we'll just click on that. And when you come to the um, simulation environment or the workspace, you realize that the cursor is now a crossbar. It looks like a plus sign. It means it's active. So if I should click anywhere and I should click elsewhere, I would have my stream placed down. Please, do we all get this part? Once the crossbar symbol is still active, once we still see that plus sign, whenever I click, it will place a stream down. So if I don't want a stream anymore, I can either press escape on my keyboard so that it comes back to the normal cursor, or if it's this way, I can press the little cursor button right above where we see material so that it comes back to the normal cursor. Okay, so now let's define the streams. We see this one has been labeled S1. This has been labeled S2. If I double click where we see S1, I can change the name. So I'll call that hydrogen. That will be our hydrogen stream. And I'll call the S2 stream nitrogen. So you just double click where the label is and then you can rename it. But how do we define the stream itself? So to define any stream, you double click on the stream. So if I should double click on this, I can now enter the properties of that stream. So we were told from the question over here that our suppliers are able to deliver the feed at the required pressure, but at room temperature. So what's the required pressure? That's 200 bar. That's what we are feeding into the reactor, or that's what the reactor is working at, 200 bar. So we know that the pressure we are using should be 200 bar. If you wanted to work in a different unit, you can click on the drop down here and select whatever units you want. So if it's kPa, you can find your kPa. If it's millimeter mercury, you can find that as well. Whatever units you're working with, megapascal, Newton per square meter, any of them. So you can just find your units there. The temperature we're told is room temperature, so we are taking it to be 25 degrees Celsius. Once again, you can change the units if you need to. And the question told us that the flow rate for nitrogen was 100 kilomole per hour. So we can put the value in here, 100, and we already have the unit to be kilomole per hour, so we don't need to change it. Now, when we are done with this part, the next stage is to define the composition. So what is present in the stream, right? So if we want, we can set this based on mole flow, mass flow, the standard volumetric flow, mass fractions, any of them at all, right? So we will keep it on mole fraction because we've already defined the mole flow here. And in that stream, what do we have? We have nitrogen and we have argon. So please remember that we're told that, where was it? We're told that since the nitrogen is obtained from it contains 0.5 mole percent argon. So there's some argon in that stream. So the 100 kilomole per hour feed, part of it would contain argon. That would be 0.5 mole percent. So the mole fraction for argon will be 0.005. That's the 0.5%. And then the balance should be nitrogen. So under nitrogen, I'll have 0.995. And then we see down here total, it sums up to 1. Right. So it's very important to cross-check that. So if we are done, we can come back to the main flow sheet. So you see the tab at the top, main flow sheets. We can come back there. So we've defined the nitrogen stream. We can do the same thing for hydrogen. So hydrogen, we double click. Temperature is 25 degrees Celsius. Pressure is 200 bar. And we were told that the ratio for nitrogen to hydrogen was 1:3. So it means that it was 1:3. So it means that we have 3 times as much hydrogen as nitrogen. So if nitrogen was 100 kilomole per hour, hydrogen would be 300. And then once again, the mole fraction, and we have just hydrogen in the stream. So the mole fraction will be 1. Please, I hope you've gotten it up to this point.
Yes, sir. Yes, sir.
Okay, that's fine then. So we've defined the two streams. The next thing to do is that we want to mix the streams and then we can heat. So for the next stages, once the question hasn't given you a flow sheet itself, some of these intermediate steps, you will need to determine them yourself based on your knowledge of chemical engineering. Someone might decide to do the heating before the mixing, right? But then if you realize that mixing it might be better before the heating, then you go ahead and do so. Okay, I think there's a question. Please, what's the question? Someone has raised their hand. Please, you can go ahead.
Yeah, yes, please. About the mole fractions,
Yes,
the
please.
1:3. We specified the one for the hydrogen, but
Yes, please,
yeah,
I'm
the
listening.
1:3. The ratio is 1:3.
Yes, please.
But yes, we specified the hydrogen to be 1
Yes, yes,
when we were
yes.
doing.
So, okay, so let me take it again. What we did was that for the nitrogen, if we say it's 1:3 in terms of the mole flow, right, it means that if I have 100 kilomole per hour of nitrogen, I'll need 300 kilomole per hour of hydrogen. Please, I hope that part is fine. So with the nitrogen, you see that we have 100 kilomole per hour here under the total flow rate. Then for the hydrogen, we have 300. So that one caters for it. What we were seeing under the mole fraction is in the stream itself. So this is for just the hydrogen stream. It's pure hydrogen before we mix it with the nitrogen. Please, I hope you get it. So the idea behind it is that because of the mole flows we've used, when we mix it, the ratio will be approximately 1:3. But then in the pure stream itself, right? In the pure stream itself, we have just pure hydrogen. You can actually decide to define it as a single stream where it's already mixed. You can do that as well. So someone might decide to do this and then say that for the mole flow, So we can make it maybe, okay, we can make it mole flow. See that maybe nitrogen is 100, hydrogen is 300. So that it caters for it directly in the same stream. You can do that as well. So you can decide to define it in one stream, or you can decide to define the different raw materials separately and then mix them up. Please, I hope you get it.
Thank you. Yes, please. Thank you very much.
Okay, you're welcome. So I was saying that we're going to mix the streams now. So we need a mixer. Under the mixers and splitters, we can select the mixer, and then we have the crossbar symbol, so it means it's active. If I should click, it will place the mixer down. Once again, I'll press escape so that it doesn't continue to place more mixers down, because if I don't and the crossbar is active, the more I click, the more it should place the block down. Okay, so we have the mixer placed down. Now, how do I connect the streams to it? You can double click on the tip of the stream. So where we see the end of the arrow, if I should double click, I can now connect it to a block. Now, for the block, we see the inlet, right? So I can connect it to the inlet over there. And we realize that it was red in color. So let me disconnect it. Let me disconnect it and then I'll show us once again. So if I should double click, realize that the arrow is red. When you see a red arrow on a block, it means that it is required. So we know that for a mixer, at least there should be two inputs and one output. So it's a requirement that there should be an input stream, right? Then the second one as well can now come here. So now this time it's blue. If it's blue, it means it's optional. So you may not necessarily need to include that extra stream. The block can still run in Aspen. So we've joined the two blocks to it. If maybe you don't want to double click on the tip of it to connect it, you can right click on the stream, the line. So you can first select it, you can right click on it, then you can click on reconnect. So you can reconnect the destination where it is going to, or the source where it is coming from. So if I click on reconnect destination, I can now join it to my block. Okay. So now we need an outlet. So I'll come back to the material stream and I'll get an outlet for it. So now that's going to be my outlet. It's my mixture of the nitrogen and then the hydrogen streams. So I'll click on escape. Right. So right now I have all of that settled. Okay. Just 1 minute. Make sure. Okay. I think everything should be fine. So we have all of that down now. We've been able to mix our stream. Now the next thing is that we want to feed it into a reactor, but we need to heat it before we do so. So how do we heat it? We'll put down a heater. So we can go to exchanges and then we can select heater. So you see we have heater, we have heat X, M heat X. So heater is just for the simple heating and cooling. It just changes the temperature for you. Heat X is a heat exchanger. So you have multiple streams. So you can have maybe a cold stream and then a hot stream. M heat X is similar to the heat exchanger, but this time you're dealing with multiple hot streams or multiple cold streams, right? So that's just by the way. So we can connect this to our heater and then we can give it an outlet. Now we need to define what the heater is going to do. So we double click on the heater. And when we do that, we come to this interface. So we can enter the temperature and the pressure. The pressure we know was 200 bar. Let me quickly confirm the values. 200 bar and then 400 degrees Celsius. So the temperature, we'll put in 400 degrees Celsius. Right. And once again, if you remember from our earlier discussions, if you see that you have this red and white mark, it means that something is incomplete. Right. The moment you do everything correctly, Aspen changes it to a blue check mark so that you know that you are on the right track. Right. So these are some of the things that you can do. Sometimes, if it's this way, you may not know where the issue is coming from. If you click on next, Aspen will tell you. So here we see that it says that temperature must be specified when flash type is temperature. So it's just saying that we're supposed to specify temperature somewhere, right? So we'll enter the value now. So now everything should be fine. Now, the thing about the block we are working with currently is that you may not always use temperature and pressure. You can decide that maybe you want to use pressure and maybe vapor fraction, or pressure and duty, or pressure and degrees of superheating or subcooling. So you can choose what you need based on the information you have, right? That's one thing. But usually you just need two things. So maybe temperature and something, pressure and something. The other thing is that you can see valid phases. So sometimes you may be working with a system that you know would tolerate some amounts of vapor and liquid in there. If it's a system that's dealing with purely vapor, right, you can set it to vapor only. If it's purely liquid, liquid only. So depending on what you have, you would know what you need to choose. But we know that for what we have, it is possible that it can become vapor, it can become liquid, especially since we have ammonia being produced at a point. So usually we just keep it under vapor liquid and it should be fine enough. So now let's run the simulation before we continue. So we can click the run button. That's at the very, very top, right? So we can click the run button and we see down here results available, no errors. So now let's check what has happened so far before we continue. Okay. How do we check the results? If I want the results, so we can get results in two ways. You can get the results of the block or the results of the stream. If I want the results of a stream, I can right click on the stream. So I'll select the stream and right click. Oh, I think I have about 10 minutes before the meeting ends. So let's just make the most of it. I can right click on the stream and then click on results. So if I do that, I get the results of the stream. So I know the temperature, I know the pressure, the vapor fraction. I can get things like the density, the enthalpy, the entropy. So I see the molar density, I see the mass density. I can change the units. So maybe I want it in kilogram per cubic meter. I can change the units and get that, right? I can get the average molecular weight. I can get the mole flow. If I need more information, I'll click the plus symbol. So I get the mole flow for nitrogen, for hydrogen, for argon, right? I get the mole flow for all of them. Or maybe I want the mole fraction. I can click the plus sign or the mass fraction. Maybe I even want to change the units to, let's say, kilogram per second. I can do all of these things, right? So these are some of the advantages of Aspen. It can give you so many details about the different properties. If I want a block result, I can right click on the block and click on results as well. So this time I'm seeing the outlet temperature, pressure, the vapor fraction, and then the duty, how much heat had to go into it. So maybe I want to change it to kilowatts so that I can see what I'm dealing with, right? We can even have pressure drop if you specify the pressure drop parameters, or you can look at the balance around the block, the mole balance, the mass balance, the energy balance. So you can look at all of these things. You can even look at phase equilibrium, right? So all these details are available to us in Aspen. Okay. So this part is fine. The very last thing we would do um before the time runs out is we'll add the reactor and then we'll continue next week. So we'll come to reactors. Down here, we see different kinds of reactors. We see R stoic, R yield, R equal, R Gibbs, R CSTR, R plug, R batch, and then electrolyzer. The first four are usually simpler models compared to the last few, right? R stoic is usually used if you know the stoichiometric relation for your system. We use R Gibbs, or sorry, R yield if you know the yield you're expecting. So you put the values of the yield in there. R equal is usually for equilibrium reactions if you have all the details. Then R Gibbs is one of the interesting ones. What that one does is that it uses the idea of the Gibbs energy, minimizing it so that you can determine the possible products you would get. So the idea behind R Gibbs is that you know your feed, right? And you have an idea of the products you're expecting, but you don't know how it will be formed or which ones will be formed at the temperature and pressure you give it. So R Gibbs will determine that for you. You don't need to worry about the stoichiometry, the yield. R Gibbs just determines the most probable compounds that will be formed based on some thermodynamic um, considerations, right? But for the particular one we are using, we'll use R stoic. So let's place it down. For the last ones, they are usually more complex. RCSTR is a CSTR, as we know. R plug is a plug flow reactor, right? Then we can have a batch reactor and then electrolyzers. But those ones require a little bit more detail. So we'll handle them later on when we come to reactions in Aspen. So let's connect our block to it. Let's connect our stream, sorry, and then we'll give it an outlet as well because it needs an outlet. Then we can double click on the reactor. We know the temperature is supposed to be 400 degrees Celsius. That's the temperature it's operating at. And the pressure is 200 bar. Now that we are done with the specification, we come to the reaction itself. So I'll click on reactions. Then I'll specify the reaction by clicking new. So the first thing I'll do is I'll put in all the reactants. So I know that I have nitrogen in my feed. I have hydrogen in my feed, the reactants, the things that are going to react. And then the products, I'm expecting ammonia. Now we need to balance it. So if we have the balanced equation, we know that nitrogen would have 1 in front of it. Hydrogen would have 3 in front of it. Ammonia would have 2 in front of it. The negative we see is because it's a reactant. So if you write the balanced chemical reaction, it should look like what we see over here. And that's stoichiometry, what we see over here, right? And then the question gave us a conversion. That's why we are using this. The question said that a single pass conversion of 33%. So we know the conversion as well. We know the balance reaction, we know the conversion. So under the fractional conversion, we'll put 0.33, that's 33% of our nitrogen. The nitrogen is just slightly less than the hydrogen in our system. For the molar extent, if you knew the extent, you could have specified that instead, right? But we know the conversion, so we'll specify the conversion, and then we can just close that. If you have multiple reactions, you can click on new and add on the reaction. So you can add maybe the second reaction. Maybe your stem is dealing with multiple reactions. There are 3 reactions, 4 reactions. You can put all of them in there. If your reactions are in series, then you check this box down here. If they are not in series, they're in parallel, you leave it as it is. Right. So now we specify the reaction. Let's come back to the main flow sheet and then let's run the simulation. So our results are available, no errors. Let's check the stream. Okay, there's a question. Yes, please.
Please, what do we mean by reactions in series or in parallel? Sorry.
Okay, if we say a reaction is in series, what we are saying is that when the first reaction happens, the second reaction follows after it. They don't happen at the same time. So maybe your first reaction happens, then the product of the first reaction might now react to form something else. So that's in series. If it's in parallel, they're happening at the same time. So maybe you have how do I show this? So maybe you have A plus B forming C, right? Then the next reaction, C will now react with something else to form another thing. That is in series. So C
Okay.
was formed first before the next was formed. But if it's in parallel, maybe you have one reaction happening, another happening at the same time. It's not like one happens before the other. Is that okay?
Yes, yes, yes.
Okay. So now let's look at the results. So we'll right click on the reactor and we'll click on stream results. So if we click on results, it gives us the results for just the block. If we click on stream results, it gives us the results for the inlet and outlet stream connected to that block. So we see the inlet to that block and then the outlet to that block, right? The names were S5 and S6. So if you like, we can even call this in and out so that we don't get confused, just so that we can see it. So the results were here. So we see them over here, right? We can see the values. We see that this is a vapor phase, vapor phase. We see the temperature and pressure. We can see the enthalpies, right? Now let's look at the mole flow. So we started with 99.5 kilomole per hour of ammonia, and some of it reacted. So we're left with 66.665. The nitrogen as well, some of it reacted. The argon did not react, it's inert, right? And then ammonia was produced. So we see that a reaction actually happened, right? So I think we can pause here for today. We have about 2 minutes left before the meeting ends. So what we'll do is that I'll save this simulation, I'll send it to us, and then next week we'll continue with adding the separators and then doing the recycle. That'll be the focus for next week. And then from there we can build up upon our understanding. So I'll just save this. Usually we save them as compound files. So we'll keep it as a compound file. Okay. But are there any questions? We have just about a minute before the time ends. So I'll send it to us. Okay. So I think if there are no questions, we can end here for now. Thank you all for your time.
Thank you very much.
Please, I have a question.
You have a question? Okay. Yes, please, I'm listening to
Please,
your question.
were we able to record the class? Some people
Yes, yes,
prompted
yes.
me that,
I've recorded
yeah,
it.
some people prompted me that they were tied up somewhere. So unless maybe we do and then send it to them.
I'll do
Oh,
that.
okay, please. Thank you
I'll
very
do that.
much.
Okay, sure.
Okay. And
Okay.
then with the videos you sent us to, hello, please. With the
Yes,
video you sent to us to, are we going to have what we did today on it?
yes, yes.
My
But
network was lagging, so okay, then I would have to follow that one too,
yes,
so that I can catch up.
okay, sure.
All right, thank you very much.
All right, thank you.
You're welcome.